All right, so just gonna get started.
Sir, the chat is disabled anyway. The chat is
Okay.
disabled.
All right, so please use question and answer if you need to communicate with. If you don't want to ask your question, otherwise please raise your hand and we'll attend to it. Okay, all right. So we are starting about 5 minutes behind schedule. Apologies for the delay. It looks like we still have people tripping in, so that kind of works as well. All right, so today we're going to talk about comparing rates. We have, in the last couple of weeks, we have gone through a whirlwind of multiple different research methods, and today we'll be talking about comparing rates. But as part of that discussion about comparing rates, we'll also talk about count data. Okay, so let's get started. So first of all, let's do a quick review of what we have done in the last so many weeks. So first of all, we went through methods that help us to describe the data, measures of central tendency, measures of dispersion. And then we went through methods that help us to compare proportions, compare means, t-tests, and all of that. Then we went to regression methods. Okay, in the second half of the course, we've sort of focused on regression methods. And for the purpose of this regression methods, we have looked at two of them. The first one that we looked at was linear regression. And we, if you remember from that discussion, we said that linear regression is essentially the fundamental, basis of regression methods. If you have a good handle on linear regression, the other regression methods become that much easier for you. Okay. Then we talked about logistic regression. And if you remember in those two discussions, this is essentially the summary of the methods, right? We said that, first of all, for linear regression, there has to be a continuous variable that's going to be the outcome, but the predictor variable doesn't have to be continuous. And we looked at a number of approaches. We looked at continuous variable as a predictor variable. We looked at binary variables as a predictor variables. We looked at categorical variables. We looked at indicator variables. We also looked at, when you have interaction terms, we looked at non-linearity. So we really ran through very quickly. So we understand that the pace of this course is very quick. And so, if you feel like you're a little bit lost, please don't hesitate to ask questions. Don't hesitate to reach out and set some time with us to go through the things that you might find a little funny, right? Then we went to logistic regression. And one of the things I wanted to very quickly say is that you might find this terminology, binary logistic regression. And really, the reason why you have that binary is because for the simple forms of logistic regressions that we teach, the outcome type is a binary variable. Okay, so that's very important to bear in mind. The outcome is a binary variable. And there are other types of logistic regression that we will not cover, where you can have the outcome be a categorical variable, okay? But just be aware that, so if you find it in the literature, don't be surprised. All right. So today we'll talk about comparing rates, and there's a number of approaches that we use to compare rates. The first one is the Poisson regression. It's pronounced Poisson. You might also think it's also a log linear regression. That's the other name that it's called. So in SPSS, for instance, I believe it's called log linear regression. But in most other software, especially R, for instance, it's Poisson. Then there are also live tables. So live tables you find more commonly in the actuarial sciences, insurance. They use live tables to sort of predict who is going to be able to pay, and they use it to, like, they use life tables to think about life expectancy of the people that they're following up. All right. So life tables have some purpose in that space. We also use it in epidemiology and statistics, but for the purpose of this course, we're going to focus more on the next one, which is survival curves. And we're going to try to teach survival curves without life tables, and we'll see how that goes. Then there's also Cox proportional hazards models that you might also find in papers in the medical sciences as well. So we'll go through very quickly. The purpose of this discussion is, first of all, to give you an introduction to the methods, help you to know when to use them, and help you to interpret the results that you find. Okay, help you to know when to use them and help you to interpret results. We will not go into as much detail about, how do you get to the, we're not going into as much detail about how do you implement the methods, okay? But that's fine, because we're just going to do this in one session, so that's okay. All right, so let's go. So Poisson regression. So Poisson regression is basically a methodology where first of all, the outcome is a count variable. So the first thing I'm going to ask is somebody to raise their hand and tell us what the count variable is. Anyone who is going to tell us what the count variable is, because if we know what the count variable is, then we'll know when to apply this methodology. If we don't know what the count variable is, then there's no point. Okay. So what's a count variable? So if you remember, in the first class, we talked about continuous variables. We talked about as being consecutive, they go, you can have decimal places. It goes 1.1, 1.2, 1.3, 4, 5, 1.6, 4.7, like that. Then we talked about categorical variables, but we also talked about count variables. So anyone who wants to tell us what a count variable is? Sorry, Tunaya, please unmute yourself. Yeah.
A count variable is a variable that does not have a decimal point.
It doesn't have a decimal point. Yeah.
Almost similar to continuous, but the fact that continuous has decimal points, there is infinite number of spaces between consecutive numbers.
Okay.
Count
what is an example?
Number of children.
Number of children. Okay.
Number
what else?
Feet.
Number of what? I didn't get that.
Feet. Number of fingers.
Number of fingers. Yes. Okay. Very good. Those are excellent examples. So you see, if you remember, when we're talking about number of children, when we use number of children as a continuous variable in the class, we said that we're just using this for, to make life easy for us, right? That the number of children is not truly a continuous variable, because you cannot have half a child, right? So we just use it for convenience. If you want to model the outcome as a count variable, like number of children, like the number of cases that you saw today in the ER or in the clinic, right? So you might have seen 50 patients today, or you might have seen 100 patients today in your clinic. But you have to remember that 100 is not truly a continuous variable, because you cannot have half a person. But you can have something like a blood pressure of 100, 110, 120, because if you remember, we said that in truth, the underlying blood pressure, okay, allows you to have decimal places. But when we measure it, we're just approximating. So when you're saying 110, the true blood pressure might actually be 110.5 or 110.1. So that decimal places allowed. So that's a true continuous variable. So that's important to bear in mind. The same thing applies to a lot of the biomarkers that you measure, like hemoglobin. If you measure hemoglobin, ferritin, a lot of things that we measure in the biological sciences that are like concentration of this, concentration of that in the blood, they're more likely to be continuous variable. But count variable are often related to like events. So how many call duty days did you have last week? That's a count variable. Okay, so when you think about it, it's not often an infinite number. Even if it is, it doesn't continue in a way that's consecutive. Okay, All right, it allows for decimal place. But if you have a count variable, the way that you will evaluate its relationship with an independent variable is with a Poisson regression. And the reason why a Poisson regression becomes necessary, why we can't just use linear regression, is because the count variable does not have, it's because of that consecutive nature that the continuous variable has. You want to create your own continuous variable from the outcome variable, the count variable. And the way that we do that is by taking the log, okay? So you're not going to take the log yourself. You're going to, so this converts the count variable into a continuous variable, so to speak. So you're not going to do that yourself. You're just going to specify to the software that you want a Poisson regression, okay? And so in the back end, it takes the log of the outcome and then models it just in the way that you would model the linear regression, okay? All right, so that's very simple, right? Very, very simple. So so let me say it again. You have a count variable, and we talked about what the count variable is, right? That the count variable does not have, it doesn't have like infinite number of small portions of it, right? Like you can have decimal places in the count variable. And the example of the count variable is often like events that happen, like how many times did you have your bath last week, okay? Or something like how many call duty days did you have last week? Or how many times did you eat a certain type of food, right? Those are count variables because you cannot do it at halftime, so to speak. Or you might have like how many people are in the class, in this class today, right? So it's either it's one person or 50 people or 51 people. It's not 50.2, right? So if you have a count variable, very important to know what the count variable is so that you know when to correctly apply this method. So if you have a count variable, then you use a Poisson regression. And the Poisson regression is a model of the log of the mean, right? If you remember that the linear regression is essentially a model of the outcome itself. So here you're taking the log of the outcome, all right? And if you're going to interpret the Poisson regression, right, the estimate that you get, the beta coefficient that you get when you model, when you do the Poisson regression, for you to interpret it, you have to take the exponential. Remember that in logistic regression, because you use the log as well in logistic regression, we have to first take the exponential to be able to interpret. So the same thing here, but when you take the exponential, it becomes a multiplicative. It becomes a multiplicative variable. That means that you have to interpret it as a ratio. So the interpretation of the Poisson regression is similar to an interpretation of the logistic regression. Questions? Any questions? Or is it perfectly clear? Keep going. This is great. All right, so let's take a question. Maybe this will bring it to life a little bit more. So you're interested in determining whether the mean number of call duty days that was done by a resident doctor. So you go to a hospital, maybe the local hospital, and then you ask the resident doctors, there's 40 of them, and you ask them, how many call duty days did you have last year? Or how many call duty days have you done during your residency? Okay, how many call duty days have you done during your residency? So you're looking at all the call duty days, okay, that you've done ever, right? So you use the Poisson regression. So you're really modeling the log of the call duty days that you've done ever. And you wanted to see whether it varies by gender, okay? So if you remember, we use this model a lot in logistic regression, but we were looking at outcomes that we're looking at outcomes that were proportions, okay? So we had like binary variables, but here we have a count variable. So who is going to give a shot at interpreting this model? Who's going to take a shot? Okay, all right. Abbas?
Good evening. So from the output, I can see it's like R output. So
Yes.
the log estimates, the intercept is a log form. So it's log 5.8 and then
Okay.
negative 0.8 for the female. It
Okay.
means that when each of the residents do have log 5.8 calls, but when it is female, they do calls.
Is it each of the residents?
No.
Is it any residents?
The constant, yeah, because it's a constant. The intercept. I'm talking about the intercept this time.
Yeah. So which residents does the intercept apply to?
Females. Sorry, females or female. All the resident doctors. Sorry.
All the resident doctors.
All the resident doctors.
Okay, keep going.
Yeah, but when it is for a, based on gender for a female resident, their number of calls, the calls they do is log of minus 0.8.
Yes. So
yeah.
So you have to exponentiate. So first of all, let me clarify one point, is that the intercept refers to males here.
Okay.
If you remember, we said that the intercept is when you set female to 0, that means that if female is 0, so here female is 1 or 0. So if you set the female variable to 0, that means that you're referring to male resident doctors. So in male resident doctors, they had the exponent of 5.8. That's the number of calls that they had during the residency. Okay, but when you compare that to males, so we're talking about an average, right? But you compare that to females, females had the exponent of negative 0.80 fold. All right, so let's stop talking a little abstract. So we've done this here, okay? So here this is the log, so we're using our output, like you said, and we are able to take the exponent. So if you take the exponent, okay, this is what you get. So 0.45 is the coefficient, and this is not odds ratio. Actually, it's a ratio, but it's not odds ratio. That's an error. All right. So basically, what you get is that the mean number of calls during the residency was 55% less. You know why it's 55% less, right? Among female resident doctors compared to males. And the way we get this 55% is that we first take this exponent of minus 0.8 and we get 0.45. So because that's less than 1, okay, because that's less than 1, we subtract 1 from it and we get 0.55. You convert that to percentage, you get 55%. We've seen this before, right? But let me take it again one more time. This is the Poisson regression, and it's a regression of the log of the mean, the log of the number of calls. So we want to see whether it varies by gender. Okay, thank you very much, Abbas, for interpreting for us. Abbas said that the beta estimate that we're interested in is this one, 0.8, negative 0.8. Okay, so that negative 0.8, we take the exponent of it and we obtain 0.45. Okay, so this is what we're trying to interpret this 0.45. The 0.45 tells us, because it's less than 1, it tells us that the number of calls that the females had was 0.45 times less compared to males, but which is also 55% less compared to males. All right, so that is how you interpret this Poisson regression. And we can interpret the p-values in the same way. P-values less than 0. Is very small, you know, less than 0.00000 up to 15 zeros or something, 1, right? And so because of that, we reject the null hypothesis that the log of the mean is 0 and conclude that the females had fewer calls than male counterparts. Does anybody have questions? Or do you want me to take this again one more time? Okay, so cold call. Let me just call someone up and say, so you're going to tell us, when do we use the Poisson regression? Anyone who hasn't spoken today wants to just raise their hands and tell us, when do you use a Poisson regression? What will the outcome be? Anyone? Okay. We have someone.
Hello?
Yes, please go ahead.
Okay. Good evening, sir. Yeah, you use a Poisson regression when you are dealing with a count protection.
A count variable as the outcome. Excellent.
Okay.
So what, give me
Yeah.
an example of a count variable that you know that we haven't mentioned today, or anyone we've mentioned today.
Well, the one I could remember was for the example we used the number of calls that were done.
Number of
Also,
calls that were done.
Yeah, the number of children. I think that was also an example.
That's an example. Excellent. Thank you very much. So that is a count variable. So before you go, can you tell us, what is the alpha in this question, the alpha level of significance that we have used?
Okay, here the alpha is 0.05.
The alpha is 0.05. Thank you very much for paying attention. Okay, all right, so let's keep going. So it's the reason why I wanted us to make sure that we get that point right is because now we're going to switch. This topic for today is comparing rates, but we started by telling you about how to compare, count variables. So, but you see, the problem is that when you have a count variable, say like the number of calls that that resident doctors have had during the period of their residency, one factor comes in time, right? So you might be comparing. So in that example, we saw that females were taking fewer calls than males, right? Overall, but someone might say, oh, maybe the females in the study had spent fewer years in the residency compared to males. So time is sort of a confounder in this case, right? Time is sort of a confounder. Time is a factor that is essentially interfering with the results that we're getting, right? So we want to use a model that allows us to account for time, okay? So what we do is that we use the same model. So if you're going to do the same question, we use the same model, but then we introduce the time factor into it. So we ask every resident doctors, how many years have you been in the residency? They tell us, right? So we have a continuous variable for time, or maybe this is in months, and so it is maybe 10 months, 12 months, 50 months, 60 months, or maybe it's in years, and it is 1.5 years, 1.6 years, 2.5, that kind of thing. So it's a continuous variable. All right, so we can use that time, we include it in the model, okay? We could also divide the number of call duties by the time. That would have gotten something like this. If you do the algebra, you get a model that looks like this, okay? So this is a model where time is introduced into the mix, and we use the log of the time as something called an offset. Not offset the guy who has that big musician, not that one, but this one is the log of time, okay? So we use a Poisson regression for rates. We saw essentially, so we have said today that we use Poisson regression for counts data, but once you introduce the time, right, the number divided by the time is the rate. So we can also use the Poisson regression for the rate. Essentially the same model. It's also a model. This is a model of the log of the rate. Okay. So when you do that for the question that we were looking at earlier, now you want to see what's the call duty days per year that the resident doctors have had, and you want to compare that by gender, whether it differs among males and females. Okay. So you have the log of the time in the model. Okay, so you see this is the model call in R. and you get an estimate that looks like this for beta 1, and an estimate that looks like this for beta 0, which is the constant, which is also the intercept. And you interpret, this is not an odds ratio, apologies, but it's a ratio, and this is what you get. So who can take a shot at interpreting this for us? This is what you get for exponentiating. So who can interpret this exponential for us? Anyone? Okay.
The estimate when it is a male resident
Okay.
is exponential of 4.86. While with the female is exponential of 0.14 minus 0.14. And using the exponent.
Hold on before you go. The exponent in the male is the estimate in the male is the exponent of 4.86. Excellent. Okay. The exponent in the female is not the exponent, the estimate in the female is not the exponent of this. The increase in the female, okay? You remember we were talking about how when you increase among male, yes, comparing to males, this is how much more females have, okay? But now because we're looking at it in the multiplicative model, right? I will say don't interpret this coefficients because you will quickly get confused. Interpret this one, okay? So here you will say that in males, males have had 129 call duty days. Okay, right?
Yes,
do you agree?
Yes, sir.
What would you say that females have had?
Why female are 14% less.
14% less. Excellent. 14% less. Okay. Females have had 14% less. So that's the way to interpret it. Males have had 129 calls. Females have had 14% less than males. All right. Thank you very much. Anyone has questions? Yes, go ahead with your question.
This 2.5% and 97.5%.
Yeah.
I guess is a confidence interval.
That's a confidence interval, yes.
But is this a 95% confidence interval?
It is a 95% confidence interval, yes. So a 95% confidence interval, okay? The way that we create it is that we first of all take the half of the 0.05. You know that the confidence interval comes from the alpha level of significance, right? The confidence interval comes from, so when we say, oh, what's the alpha level of significance, 0.05, that is where we derive the 95% confidence interval from. So, because essentially 95% is 0.95, okay? So, and that's 0.05 and 0.95, you make 1. But the 0.05, we don't just apply it directly. We first of all take the half of it, one half at this extreme, the other half at that extreme. So that means that what we're really doing is that we're taking 2.5% at one extreme, 2.5% at the other extreme. So, you know, like, so if you did this experiment many times, okay, and you get a normally distributed curve that looks like that, right? The estimates that are in the lowest 2.5% and the estimates that are in the highest 2.5%, remember that the highest 2.5% is 97.5. That's how we get this number. That is 95% confidence interval.
I understand now.
Excellent. All right. So anybody have any other questions before we move on?
Yes, please.
Okay. Abbas.
What is the p-value? Is it the exponential?
No, we don't exponent. No.
Okay, 2 raised to power minus 10 minus 16.
Yes. 2 times 10 raised to power minus 16.
Okay, thank you.
Okay, excellent. Any questions? So we have more than 50 people in the class today, but I have only had 4 people speak up today. So I want to hear from other people.
Someone wants you to go over the interpretation again.
Okay, all right, thanks. Yes, let me do that. So this is it. This is the interpretation again on the next slide. So basically what we have here is that we have an estimate of negative 0.15, okay, minus 1.47401. This is the estimate when you model the Poisson regression for rates. I remember we said that we have included the log, okay? So the first thing you do is that you take the exponent of the Poisson regression of the beta estimate that you get. So this is beta's 1, and this is beta 0. This is beta 1, okay? Now, if you take the exponent of the beta 0 and the beta 1, you get these two numbers. You get these two numbers, okay? Now, which are down here. Now, so if the exponent of beta 0, which is 4.80, that S exponent is 129.5. And we said that because this female variable is 1 if it's female, okay, and 0 if it's male. All right. So the way that we interpret a binary variable in a regression output is that for the intercept, you set this to 0. So you take the 0 for this one and say, if female is 0, that means that that individual is male. All right. So we say that on average for males, 129 is the number of calls that they have had during the residency per year. Okay. 129 is the number of calls you've had per year. But for the female, we say that the number of calls they have had per year is 14% less than the number of calls that males have had. And the reason why it is 14% less is because we take this 0.86 and we look at it, say, oh, this is less than 1. And because it is less than 1, we subtract it from 1. So 1 minus 0.86 is 14. 1 minus 0.86 is 0.14, which when you convert it to a percentage, right, is 14%. So that 14% is easier it's easier on the mouth, right? It's easier to wrap our heads around. And you say that the call duty rate in females was 14% lower than the call duty rates in males. Okay, so this it's easier to sort of engage with when you say 14%, so that you can imagine that if on average in another population, the number of calls that are happening in males is X, then the number of calls in females is 14% less than that. Okay, I hope that's clear. Because we'll take another example, and I want somebody else to take the lead here. I'll just set the stage and say that basically this is a COVID-19 question. So you want to see the daily COVID rate. So because remember I said it's a rate, so that's why we're using the log of the rates, and that's why we're bringing the time into it. Right, so you want to compare the daily COVID rate in the urban centers in your country to the rural centers, okay? So on average, so you want to compare the urban centers to the rural centers, say in the first weeks of the pandemic, 6 weeks of the pandemic, something like that, okay? So you then have results that look like this, but I'll go, so who can tell us what this is? Is this a beta 1 or beta 0? Anyone else who hasn't spoken today wants to tell us, is 0.1615759, is that the beta 1 or the beta 0?
Zero.
So I think Madia is going to go first. Okay.
Okay, 0.16 is the beta 1.
Is the beta 1. Excellent. Okay. So what does that mean? Is it the what is it? Is it the increase in, is it, sorry, not the increase, is it the, yeah, so let's, it's going to get complicated. Let's go to this one, and then you can take a shot at interpreting for us. We have the exponent to be 1.17 of 0.158. Okay, so can you try to interpret for us?
The exponent is what? I can't see it on my screen.
Is 1.17.
Okay, if the exponent is 1.17, the exponent of urban or the beta one, right?
Yes, of the beta one. Very good.
0. Come again, please.
Is 1.17.
1.17.
Yeah.
So 1.17, 1 minus 1.17, that will give us a negative value of minus 0.17, right?
So wait, the first thing you have to decide is 1.17 more than 1 or less than 1?
It's more than 1.
Okay, so if it's more than 1, then you cannot use the minus. So if it was less than 1, you use the minus approach that we used earlier.
Okay.
Okay, but now that it's more than 1, then it means that you will just say that the daily COVID rate in the urban centers is 1.17 times the daily COVID rate in the rural centers.
Okay, understood.
Okay, so let me take that again. If the exponent is less than 1, if it's less than 1, you subtract it. You subtract it from 1. You say 1 minus 0.86, like we saw earlier. But if the exponent is more than 1, okay, if the exponent is more than 1, we don't subtract. We just say that the daily COVID case rate was 1.17 times in the urban location compared to the rural one. So sometimes you might use 17% more, but this 17% more, it can quickly get you into trouble. Okay, the times when you will get into trouble, and that's why it's not the best, it is when you now have a value like 2.17 times or 5.17 times. So you have to, so the one thing to think about is that we have, when you have a rate like that, you have people going from 0 to 1, which is just, it's bounded, right? You cannot have less than 0 if it's a ratio. But beyond 1, it's not bounded, it goes into infinity. So that's why this is not the ideal, right? It's better to use this one when it's greater than 1. Okay, you just say 1.17 times in the urban location compared to the rural one. I hope that's clear. I hope I haven't made it more complex for you. Anyone else have questions? Because we're going to switch from Poisson regression. All right, so things to note, as we have seen in linear and logistic regression, we can control for confounding in Poisson regression. We can look at non-linearity. We can evaluate effect modification. You know, basically the general principles that we looked at in linear and logistic regression, you can do here as well in Poisson regression. We're not going into those details because we just want to get the fundamental of, you know, what is Poisson regression? When do you use it? How do you interpret? Everything else, the way you control for confounding, the way you evaluate effect modification, the way you select models is the same as what we have seen in linear and logistic regression. Okay. All right. So again, quick, this is just updating the table that we just saw. That first of all, right? First of all, in the linear regression, we're looking at whether whether beta 1 is 0, whether there's a difference between x, between the variable, whether for every increase in one variable, to what extent do you have an increase here? In logistic regression, we had a binary 0-1 variable, and the null hypothesis is a difference in the log of odds. For the count, the null hypothesis is a difference in the log of the mean. For the rate, the null hypothesis is a difference in the log of the rate. And these are the model equations. We've seen this before. So any questions before we move on? Any questions at all? I see a few hands up. I just want, if you want to talk, if you don't, there are hands that have been up before, so. If you want to unmute yourself, otherwise we can keep going. All right, so going, does this mean that that Poisson regression is perfectly understood? We know when to use it. We know how to interpret it. Okay.
Billy, can you emphasize that the output in the Poisson, when you use a log of time, is actually the rate, as opposed to say women did 14% less calls than men. It's can you talk a little bit about why it's time bound and why it's rate versus just maybe a count?
Right, yeah, so thanks, Abua. So basically the reason why it's a rate is because in this case, we have introduced time into the model, okay? So thanks, Abua. We talked about it earlier, but good to emphasize it again. Because we have introduced time into the model, in this case, you're going to say that the rate in the variable in X group that you're looking at or interested in compared to the reference group. So in this case, it is the COVID case rate in the urban centers compared to the rural centers. It's not the number of cases. It is the rate, right, in one group compared to the next. And you know, if we didn't have the time, then it will be the number of cases. Okay, it will be the count. Okay, excellent. So now we move on to the next section.